అందరికీ నమస్కారములు. Today is 3rd August 2023, Wednesday. It is a good day for all of us that we have completed 1 month of course instructions, coursework on the second advanced level, first advanced level 2 course on certificate course on Sanatana Dharma. Now we are going to start with the second month with a new topic, that is Vedic mathematics by Gautham Mukherjee ji. He doesn't need any introduction to all of you. He is one of us. He taught us all 3 basic courses, the Vedic mathematics, and also he is well known to us in our class. Now let us start with reciting Vande Mataram and Prarthana. After that we will hand over the platform to Gautham ji. Chala Chittibabu garu.
Vande Mataram, Vande Mataram, Sujalam Supalam, Malaya Sitalam, Sasya Syamalam Mataram, Vande Mataram, Suprajosna Pulakitayamini, Pullakusumita Drumadala Shobhini, Subhasini, Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Vande Mataram. ధన్యవాదములండి చల్లా చిట్టిబాబు గారు. Now let us request Anantanji to do Prarthana, please.
Sarvebhyah namaskara. Hari Om. 1 minute meditation. Let us close our eyes. Sit erect. Total concentration on breath. I don't interfere. Just I watch it. Visualize my body like any other object. Trivaram Omkaram. Gananantva Ganapati Gum Havamahe Kavim Kavinamupamashravastamam Jashtarajam Brahmanam Brahmanaspata Anushrunvannoti Visidhasadanam Mahaganapataye Namaha Prano Devi Saraswati Vaje Virvajinivati Dhinam Avitriyavatu Vagdevyai Namaha. Gurureva Gatir Gurumeva Bhaje Gurunaiva Sahasmi Namo Gurave. Na Guroh Paramam Shishurasmi Guroho Matirasti Gurau Mama Pahi Guru. Jnananandamayan Devam Nirmalaspatikakritim Adharam Sarva Vidyanam Hayagrivam Upasmahe. Shruti Smruti Purananamalayam Karunalayam Namami Bhagavat Pada Shankaram Loka Shankaram Shankaram Shankaracharyam Keshavam Badarayanam Sutra Bhashya Krutau Vande Bhagavantau Punah Punaha. Ishvaro Gururatmeti Murti Bheda Vibhagine Omavat Vyapta Dehaya Dakshinamurtaye Namaha. Om Sahana Vavatu Sahanau Bhunaktu Sahaviryam Karavavahai Tejasvinavadhitamastu ma vidvishavahai. Om Shanti Shanti Shanti. Harihi Om.
ధన్యవాదములండి అనంతన్ గారు. Now let us request Gautham ji to start the webinar, please.
सभी को नमस्कार.
నమస్కారం అండి.
To all. Can you see my screen?
Yes. Introduction to Vedic Mathematics level 2.
So we start with the revision as was there. So we discussed earlier all these different counting procedure and mathematics, how the mathematics started with counting, and various symbols, Roman symbols were used for this thing, but seriously, calculation part was not there. That much was not flexible. Only when there is a concept of cardinal and ordinal numbers also, which is something called marking the things or labeling certain things. It's called one of them cardinal numbers, and ordinal numbers is a number that tells the ordinal numbers, and cardinal numbers are the way the numbers of cardinal numbers are the thing which meant for calculation, and ordinal numbers are just for like roll number and so on. These are just leveling, one first, second, third, etc. And then when mathematics starts basically with the positional number system of India, where the digits are 10 digits were used initially, and there are initially 9 digits were used for counting, and then the requirement of 0 was felt, that when something is not there, missing in the position, to denote that there is a big hollow circle, that is the discovery of 0. But actually the discovery in India was the positional value itself, positional number system itself, because depending upon the position, the number is determined. So this we discussed earlier in this thing. And finally 0 also, along with other numbers, 0 also took part as part of calculation, and this there is a history for that. We discussed on that in our earlier course. Now the base actually is 10 in the decimal system, but later when computer came, there was a need of base, change of base, like binary, because computer understands only 0 and 1. That's 2 numbers. So binary was the pretest for that, and then group, when they are grouped in 3, they are called octal. When grouped in 4, they are called hexadecimal. There also similar mathematics are developed using all these bases, but we will be confining our discussion with decimal, although all the procedures that are used in Vedic mathematics can be equally be applied with other base systems. Then the concept of place value and face value, like here in 756, place value is this unit, 10, 100. These things are place values. Those are the values of the vacant places, you can say. And the 756 here are these face values. Now, face values, normally normal numbers, the face value and place value, both are positive. Whereas the negative place value, this is already used in all mathematics, modern mathematics. Those are called fractions, like 10 to the power minus 1, 10 to the power minus 2, and so on. Like 0.34 here is written as 3 into 10 to the power minus 1 plus 4 into 10 to the power minus 2. So negative place value was known. However, in Vedic systems, negative face values are also used. Those are called vinculums. And those are vinculums makes calculation easier in some cases. When these negative face values are used, the calculation becomes easier, and so that will be shown. Now, numeric symbols throughout the world, there are numeric symbols used, and hex code means that to handle in computer, what are the codes for that, those symbols. So the list of the symbols are there in various Indian languages. There are various, you can find out the Telugu also. There are this row. There are symbols. We find Bengali, all these things. Although this font is not very good, but nevertheless, these symbols show that Indian languages symbols. Similarly, there are some other languages where also the decimal system, I mean the positional number systems are used. Those are also given here. English, of course, is positional number system. Arabic, Thai, Lao, Tibetan also are shown here. However, in Chinese, there are some number symbols, but those are not actually meant for calculation. They're not coming in this decimal positional number system, so these are not listed here. Now, what is Vedic mathematics? Vedic mathematics were actually started with 16 Vedic sutras and 32 sub-sutras, and 13 are also not to be used after that. Now, various alternative mathematics. We learned mathematics, but there is a particular algebraic background is there for all these whatever procedures we follow. We follow some procedure of addition, subtraction, multiplication, division, say LCM, DCF, all these things. So there is always in background algebraic method is there, algebraic procedure is there, using which we are following that procedure. We without knowing that, sometimes without knowing any algebraic background, we just from our childhood we started practicing these procedures, seeing each other. So some teacher taught us, or our parents taught us, and how to add, how to subtract, multiply, divide. So this we learned from just from by seeing each other, but always it didn't get concerned with the algebraic background of that. It is not required also at a particular level, up to a particular level. Now, whenever if we change the algebraic background between, we can even have more other procedures for all these multiplication, division, and so on. So this doing various things actually develops a mathematical intuition instead of doing just mechanically things. And moreover, this Vedic mathematics sometimes people use as an alternative, or sometimes as a sort of mathematical magic or this kind of thing. Also, this is not very much recommended. it is actually serious as all others we learned from our childhood, those procedures. These are parallel procedures, you can see. Vedic mathematics gives alternate procedures. So there are, these books were very good book actually. This is maybe that earlier whatever development in Vedic mathematics were not very, we have not much way to know that. This this Rishi, Bharat Krishna Tirtha Ji Maharaj, he actually, when he dug out all these things from Vedas. Also, he formulated his own actually because of his mathematical intuition. He gave many refined, you can say, refined all this. Very seed was there in somewhere, but he from that seed he dug out the meaning of that thing and he practiced those things for several years. And finally, he wrote this book, and it's a very good book. I gave the reference earlier, and I think many of you may be possessing that book already, and maybe following also. So there are actually these 16 sutras, and there are sub-sutras, 13 sub-sutras, and some meanings are there. Actually, we didn't cover all these things earlier because so many things are there, like even in addition to the normal, the subtraction, addition, subtraction, multiplication, division, there are others like solving equations, even differentiation, integration, all these things were there. And Chalana Karanabhyam, it is actually related to differentiation. In this course also, maybe differentiation in this course we will not be covering. If time permits, we can have a small introduction of how it is being done, and let us see how it goes. Actually, how the students understand. Then we can give an introduction so that in the third level we can have a better, equation and all these things can be covered. So there are so many formulas, and so these are all can be a matter of study. Even somebody can do self-study of that. In this course, we will be adding the square root thing and some other procedure of division called state division. Now, as earlier we discussed that addition, subtraction, multiplication, division, these are taught in school, but algebra, if the algebra is already told that algebra is changed, the procedure or method will be changing accordingly. Now, in as I told the Vedic mathematics uses negative phase value. What is negative phase value? When some digit becomes more than five. So handling that becomes a little difficult than digits which is less than 5 or equal to 5. So why not express the digits? Say 48 we have, 8 is more than 5. Why not use a negative phase value and increase the previous digit to increment to 1 more and use a negative suitable negative phase value so that the value actually becomes 48. Here actually 50, as I know, 5 into 10. And if the negative phase value unit, so here it was 4 into 10 plus 8. And here the meaning is 5 into 10 minus 2. So this results into same number called 48. So, but the handling 8, handling this minus 2 is more easier than handling 8. So that we have shown in the earlier, this called using vinculums. Here we have given examples, certain examples we have seen that how that multiple digits are there and how those things can be made vinculum and each other. So whenever you see that we have like the original number of 142,857, but here we can write as 143 and 143 whole over bar 97. We can use it 100 minus 3, so 1, 0 and 3 bar will give these things. So likewise, there are some examples given. So in the next slides, negative phase value, and this was high. And using vinculums, in case of multiplication, we have to use only 5 into maximum 5 into 5 table will be required. And additions were shown here, that how instead of doing large numbers like 8 plus 9 plus 7, 8, here we have seen that how this -2, -1, -3, -2, this can be easily added, and then finally after adding, this again can be transformed into a normal number by formula using to each other. We have already shown these things. So any clarification is required here? Any detailing required? Actually, these are all revisions. Anyone have any question in this?
I think you can go ahead. There
Yeah.
are no questions.
No. So these are the thing. These are easy actually. So it is a mixture of these things. Same. It was actually a example where the whole thing can be put on under a bar, and here there is alternative things that how the bars are whenever required. 38, it is 4 and 2 bar, and then it can be done so on. And now here is an example that normally people use these shortcuts kind of things. No problem with shortcuts, but these are actually showing as if the shortcut methods are only emphasized here. There is a background, of course, there is a algebraic background is here, but these are not Vedic mathematics is not limited to such small things, shortcuts. Here, multiplication, repeat the multiplication in a near a base. So certain numbers, like say we have to multiply 97 into 93. So using conventional method, it looks very complicated. So here you see that it is only from the nearest powers of 10, which is called base. It is only 3 shortage. It is 7 short. And using this 3 and 7, we can easily multiply it to 21. And then there is a cross subtraction is there. 97 minus 7, so it becomes 90, or 93 minus 3 becomes 90. So this becomes the easily you can find the multiplication product. So here you see that the same digits are used, and where you see that it is a nearest tens power, the base is actually only increases by tenfold with the same numbers, and we find that it becomes equally easy whether we use it is near to 100, 1,000, 10,000, and so on. So if some other numbers is put, and wherever if these things are, this part becomes bigger, we can again subdivide it into another problem where separately we evaluate these smaller parts. This like these different steps. This can be easily used, and as you've seen that increasing more numbers of 9s in both multiplications results in addition of same number of 9s in the first part and same numbers of 0 in the second part. Here in this example we have seen. So this, if I repeat, actually this is 3 into 7, 21, but you have to keep the same numbers of digits so that it will add actually. The algebra also requires that. And this is 9997 minus 0007 becomes 9990. And this becomes the whole result becomes, which were earlier very difficult, 999, multiply 9997 into 9993. It becomes 9990 0021. It becomes very transparent and easy by this method. And the algebraic expression of this is that this expression, if we express in this form, where you take out n, capital N, this base here is 1,000, 10,000, and so on. So this, if you take out, it becomes like this. Already there is something n minus a. These are n minus a. This is n minus b, for example. And this becomes, when I subtract this cross subtraction, it becomes n minus a minus b. You place it here in the left, so that similar, these many numbers of digits are already multiplied. But multiplication of n actually signifies placing it in the left part. And we add with that simply multiplication with the deficiencies. So it is this way. Similarly, it is done for, which is, these examples are below a base, and these are above a base, above base, and above base we show in a similar way. And here also we just add these things and it becomes like this, and they multiply. So similarly, the algebraic expression becomes like this, all with plus. Okay, I think it was clear. So this also becomes easier. Here also we shown that a greater number, if bigger numbers are there, we can easily again subdivide. Here it comes that when concept of vinculums will be required here, because one is below a base and above, other is above a base. So minus into plus becomes minus. So it is we denoted by vinculum, and it becomes 93 plus 7, or 107 minus 7, it becomes 100. And we have to finally clear the vinculum, and the answer becomes like this. So more examples are given here. And here the explanation says this one is plus, one is minus. Accordingly, you do plus minus, and we finally do subtract into this part, the deficiency and or excess with the base. So we did like that. Now here sub-base concept came. In the sub-base concept, we do not, it is not a near to a power of 100, but a fraction of a power of 100. Now here, what we did, we found that it is sub-base is 100 in both cases. Let us first check base as 1,000. Either I can use this 1,000 as a base, or 100 as a base, or multiple or some multiple of a base. So 483 becomes, it is 17 short from 500, it is 3 short from 500. We multiply. But finally, we this base, we again divide, because it was 500 was half of this. In case of 100, what you do, you multiply by 5, because 500 is 5 times more than 100. So finally, the result becomes the same. So similarly, it is above sub-base was shown, above sub-base, and one above and another below sub-base was there. There is a little more, in case of when there is congested, I mean, less base is there, there is some issue of carry. This carry has to be tackled properly. Here it is no carry was required. Here is just with sub-base we get. But what is the explanation of this sub-base was given here? If it is m times something, m times a base, this is a capital N is a power of capital N is a power of 10, which is base, and then m makes it sub-base. M into n becomes a sub-base. Mn minus a and mn minus b. So mn takes out. So this m actually you are actually handling this. Here multiply by n, shift to the left digit. So many left digits, but finally this m actually is this here, for example, value of m is 1/4. So we are dividing by 4. Here also, here you dividing by 2. And there are so many issues were there. If the at some point some digits becomes half, that half actually becomes 50. Value of the half becomes 50. We discussed in this thing in details, why it becomes like that. Any clarification, or at the end we can do it? Just note it down that in certain this some points you required clarification. You can use discuss it later. Now you quickly go through the revision part, and then. But still, if you want to do something, you can raise hand. That can be opened again. But this discuss can be opened. Now, the more general multiplication was used, Tirjak method. And you know, this Tirjak method, I read a paper that with respect to conventional multiplication that we do, this Tirjak method, Urdhva Tirjagabhyam, actually, this sutra was Urdhva Tirjagabhyam, upwards and slant. So here the grouping actually is different than what we normally use. We group all the units, all the tens, all the hundreds, etc. But in our conventional mathematics, we didn't do that. We first we multiply this D with all these things, and again C with all these things, which is shifting towards left. So that and we finally add. So it is seen that those numbers of micro steps. See, actually, computer works on those micro steps. Each step actually requires also some in assembly language. Language is called processing. Each of these things in microprocessor, all these things require each processing. It is found that this method actually requires less number of processing, so therefore it becomes a less delay. And then all the devices presently that is used, say mobile, laptop, everything requires a lot of multiplication all the time. Say even to suppose I am moving this, see the mouse pointer. Even for moving the mouse pointer, so many calculations are being done in the background. Where to place the mouse pointer? So if in the micro level, if the each multiplication takes less time, so processing time of the whole computer or mobile becomes less. So therefore, Vedic mathematics, some people tell that Vedic mathematics, what is the use of mathematics when we have calculators? I say the opposite way, that the very use of this calculator devices, these devices will becomes more efficient if we use Vedic mathematics in the background circuit. So Urdhva Tirjagabhyam is like that. First we multiply units, so it becomes 3 into 5 becomes 15. So we place that carry in the left in the next digit, next row. And for the 10th digit, I have seen that this AD plus BC means this into this plus this into this. So 4 into 5 plus 3 into 2, it becomes this 26. We place like this, and then finally 4 into 2 becomes 8. So here, finally we add this carry we have given here, and it becomes answer. So if we increase the number of digits, it becomes more complicated, but with practice, this becomes easier. Here you see that if we these 2 digits, see any number can be expressed as we have seen in the decimal system, that is actually basically are unit, 10, 100, and unit, 10, 100. If those 2 things are multiplied algebraically, then if we group them, it will become unit, 10, 100, 1000, and 10,000 in this case. So here we find that as we go towards fringes, when both the sides, the number of terms becomes less and less. But in the middle, more and more terms. Here, these units and the 10,000 both have only 2 digits involved. In the 10 and the 1000, we have 2 plus 2, 4 digits involved. And in the middle, we have 6 digits involved. So it is like this straight, I have seen that this straight, this is also straight. These are only one cross is there. This three lines cross is there. So these are examples are shown here. So here you have seen that unity is 4 into 8 place here. Here you see that this tens digit is actually 1 into 2 plus 4 into 5. 1 into 2, 4 into 5, like this cross. So here is 22. See, this becomes 22. 22 here. 2 place here and 2 we place here below this. And then this becomes actually multiplication of, multiplication, then adding up 3 terms. 3 into 2, 4 into 3, plus 1 into 5. So this total is 23, and then 23 is placed here. And this becomes 3 into 5 plus 1 into 3. This becomes 18. You place it like this, and finally 3 into 3, 3 into 3, only 1, 3 into 9. Finally, when we add, we get these numbers. It's a matter of practice, actually. Actually, instead of writing, you have to all memorize. Actually, these are small numbers. Moreover, I have told you that if digits are more than 5, you can convert it into vinculum. Here also, if suppose instead of 314 is 318 is given to you, you can easily write, instead of 18, you can write 3, 2 and 2 vinculum, and accordingly this vinculum, this will be minus. You have to, with practice, you can even memorize. In the memory, you can do it. The numbers should not be bigger, would not be very big, so that you can easily remember them and put them down. Bigger numbers are used, so it is becomes more and more complicated, but nevertheless, it can be done. So the same example I have given with a little sparsed in the past present. Here, yes, here actually whole things are described here. So more and more terms are being introduced here. If we express it in this form, you'll find that there will be 2, the 3, there will be 4 also, 5 also, and so on. 4, 5. It will be like, in this case, it will be 1, 2, 3, 4, 5, 4, 3, 2, 1, like that. So there's a 1, 2, here you see 3, here 4, here you see 5, and again 4, 1, 2, 3, 4. 4 here is 1, 2, 3, 3, 2, and 1. So if we can algebraically express, it will come like that. And this is looking very cumbersome, and digits are mixed here. So therefore, we have made it sparse like this. So 1 into 2 is 2. 3 into 2 plus 1 into 4 becomes 10, like this. 4 into 2 plus 1 into 6 plus 3 into 4 became 26, like this. So this placing is done properly and then finally added. What we have seen, we see that in this example, if we express which more than 5 is there, we express as vinculum. The carry part, where the carry was 1, 3, 5, 5, 4, 2, and 1, only 2 carries were there. 1, because something was 10 and something was 16 here. So these carries are put there. So finally, it becomes certain numbers become negative, and if we clear the vinculum, it becomes give the same answer. So you see that Gautham, this way you can do. You can note down if you needed any clarification. Now we compare between different multiplication methods. Suppose I've chosen purposefully these bigger numbers. So with Gautham, this becomes like that. But we know carry up to 100 is required here in this case. But we transformed it to vinculum. It is not using vinculum and using vinculum. Using vinculum, it becomes very easy and very straightaway actually. Minus 1 into minus 2 is 2. Sorry, minus 1 into 2 is 2 plus this becomes 2. Sorry. Minus 1 into minus 2 is 2 and minus 1 into minus 1, 2 plus 3 and then 0, so it becomes 3. So this way, if we see that if we all keep that plus and minus and subtract accordingly, subtract or add, so this finally becomes this one. Whereas in Nikhilam Navatas Charamadasata, we may express it is as nearest this powers of 10 and with the base is 1000 here and it is 100 elements short, it is 102 short. And for 111 and 102, again, as I told, it is just subdivided into another place. And I find out that it is actually 111 plus 2 is 113 and 11 into 2 is 22. So this 11, because there are only 3 places, so 322 place here, this 11 we put as a carry. So we finally, when you add, it becomes, it is not, I think it is looks very easy compared to this in Nikhilam. We compare with a conventional method. A conventional method, just conventional, we use big numbers to multiply, to remember, and then 8 into 9 and 7, 64 plus 7, 60, and so on. You do like that. You memorize also. There also you in the memory you do not put 6 and 64 and so on. But 64 plus 7 carry we add. There also military calculation is there involved, and we finally arrive into this result. Whereas in conventional method, if we use vinculum, it becomes a little easier. With 0 become instead of 0, this we didn't put, so that 0 part only the shifted two places. Shifted 2 places equivalent to this 0. So here we add these things and finally we arrive into the same result using conventional method using. So we compare the multiplication algebra. Here in the conventional method, we used like this. The first line we use this. 2 numbers are this and this. One ABC and PQR. So in the first row, top row, you like this, and then you in the second line you use this, but shifted, place is shifted towards left. And then third line you use this and place further shifted to the left, then all added. Whereas the Urdu Trijagabham, we have we group it towards very beginning, unit 10, 100, 1000, and so on, 10,000. So this way we did, it we told earlier. Trijag method has been proved to be more efficient through research, in using calculation in terms of in case of computer. Now you come to division. Here we first started with a very easy form of division, namely divide by 9. The main idea of this Nikhilam method of division is that here we don't have to use tables. Rather, first we see that had we divided, instead of 9, if we divide by 10, what will happen to that? We are dividing 34 by 9. Okay. But suppose we divide by, first of all, see that the purpose of this division is to find quotient and remainder, not going up to fraction for the time being. Now, if we divide 34 by 10, we just put a line and that becomes our division line between the remainder and the quotient. Remainder on the right side and left side should be the quotient. But we are not dividing by 10, we are dividing by 9. So how it happens? What will happen that? Like for each 10, one extra 1 will be there. So between 0 to 10, there will be one extra. Again, in that block of 11 to 20, there will be another extra 1, and again after that 3, there will be one more extra 1. So this, we add this extra ones and it add with that remainder, it becomes the remainder. In this case, our question becomes same, but remainder is added. So basically, what to do? 9 is deficient from 1 as 10. Simply, you just put it down. This 3 you put down. This is the procedure. But the background is there that in every you can say that, sorry, in every block of 9, there will be one extra will be there. This 1 will be extra. Every block of 10, So 1 to 10, 1 to 10, 10 to 1 to 10, and the 11 to 20 and 21 to 30. So the 3 numbers of ones are there. Those are added here. Okay. Every block of 10, I'm sorry. I was told it correctly. Similarly, 61. Here, every block of this 10, it becomes 6 becomes extra. So 6 into 1. Actually, I didn't write this 1. Actually, 1 is there everywhere. 6 into 1 is 6, and the 6 plus 1 becomes 7. So here, suppose I comes to 1, 2, and 3. 123. So had we divide by 10, it will become as 12 as quotient and 3 as remainder. But here, what is happening? Here, for this 100, one total 10 has come here in the quotient itself. And then this becomes a total quotient of digits of 13, 3. This 3 becomes added to this remainder as well. So the remainder we added to 6. So the procedure is this 1 into 1 is 1 here, 2 plus 1 is 3, and put 3 again. This 3 into 1 is 3. So it becomes 3, and finally we add. This becomes total remainder becomes 6, and this total quotient becomes 13. Here in this case, 253. So because of 200, we get 20 extra, 20 extra, and this becomes the 2 extra for the quotient. And then again 7 extra because of this, and then we finally add. But here, when we add, it becomes the remainder becomes more than this divisor 9. So again we do, and finally the quotient is added to 1. Any question in this case? Anybody raise hand? So we proceed.
Yeah,
Gautam
please
ji.
proceed. Please proceed.
Gautam ji, this 25 by 9.
253 divided by 9.
Yeah, 253 divided by 9. Can you explain in a
Once more.
systematic way? Yeah. When about the moment you say 1 more 10, 1 more 10, and 1 more 10, that becomes a bit of confusing. So practically, how do we attempt this? For example, in the initial cases, it was very clear, but here there was a bit of confusion. So can you please-
123 was any confusion?
No, there's
Ah.
no confusion there.
Non-confusion. Because this remainder 6 was less than 9. There's
Right.
no problem. But here it comes actually, it may come that this remainder becomes more than the divisor, more than 9. So this is 10. 10 remainder. Suppose 27.
No, that part is understood. I mean, the initial part, 27.
Is understood. Yes.
That,
Because 2 is there and 5 plus 2 is 7 and finally 7 plus 3 becomes 10.
okay.
But
Okay.
10 actually means that
Right.
it becomes 1 remainder and 1 will add towards quotient. So that is being done here.
Right. Now I understood. Thank you.
So it is as if suppose I put divide 10 by 9. This 10 by 9. So 1 we put here and 1 will be quotient. I could have put 1 here, but actually 1 quotient I am putting here. So therefore we added here. When actually we shifted this 1 from here to here. Had we given only this part, suppose only this part, suppose what's going on? Yeah. Suppose my problem was on only this. I would have wrote the 1 here. No, I mean, no 1 here. I mean, in my result line. Yes, not here. Suppose my problem was only this, dividing 10 by 9. I would have added here, and this 1 you have to anyway you have to come here. So had we divide 10 by 9, I would have gotten 1 as quotient and 1 as remainder. But I didn't write this 1 here. Instead, because this 1 is contribute towards quotient, I directly added to this 2. Is it clear now?
Yeah. Thank you. All people, I mean, the students who are listening, they wanted revision, but they are not raising any questions.
I think it is they practice it and so on. They do not have any.
Fine, very nice.
Suppose anyway they are noting it down and then they can ask anytime. I can go back and answer. Division by 9 for bigger numbers. Division by 9. So again that only 1 is there. We do not see this 1 because always you are multiplying by 1 only. Here purposefully just taking a very less numbers. Otherwise it will be even complicated. I mean, not complicated. You have to divide it into. We cannot write in one line then. Maybe you have to use multiple lines in that case. So here it is simple way. A number is given 12312. 12,312. Had we divided by 10, this 1231 would have been my quotient and 2 as remainder. So, but 9 is 1 deficient, so it will keep on adding. So 1 into 1 is 1. 1 plus 2 is 3, and 3 into 1 is 3. 3 plus 3 becomes 6. 6 into 1 is 6, and 1 plus 6 is 7, and 7 is put here as a remainder. So 9 becomes my total remainder. We add up all these things, and finally we get 9 becomes my. In this step, we get 9 becomes remainder, and 1367 my quotient. But 9 is same as this one, and so 9 will contribute 1 towards the quotient, and 0 will become the 1200212. Basically, it is 12,212. So we dividing line again. Had we divided by 10, again we do 1 into 1 is 1. This 2 plus 1 is 3. 3 becomes 0. 3 again plus 0 is 3. 2 plus 3 is 5. 5 plus 1 is 6. So this becomes finally we add these things and this becomes my quotient and this. 1011,649 means actually it is 10,11,649. So here it becomes more. You have seen that 13 becomes finally my 1 and 1 put here. 1 plus 0, 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 6, 9, 9 plus 4 is 14. 9 plus 4 is 13. And this becomes 22. Again with 22, you divide into 2 and becomes 2 and 4. This 2 gets added to the quotient and 4 becomes my final. Earlier we did a similar fashion, we are doing it here. Where is again divided into 22 will become divided. Now comes to division by 8, 7 and 6. 8 actually it is in every 10 there will be 2 extra, means it is 2 less than the nearest 10. So here also this 2 into 2 becomes 4 and 4 becomes 7. 2 into 3 becomes 6, 6 plus 1 is 7. 3 into 1 is here in case of 7 it is 3. 3 into 1 is 3, 3 plus 2, 4, 5. 3 into 2 is 6, 6 here. Here the difference is 4. 4 into 1 is 4, 4 is quotient and remainder. 234 divided by 8. This 2 into 2 is 4. 4 plus 3 is 7. 7 into 2 is 14. 14 plus 4 becomes 18. And this quotient becomes 27. But 18 again only contribute 2 as a remainder and 2 as a quotient. So finally, because 16 fits here, so this 16 will give 2 in the quotient, and the remaining 2, 18 minus 16 is 2, and it becomes 2 as a remainder. 345 divided by 8. 2 into 3 is 6. 6 plus 4 is 10. 10 into 2 is 20. 20 plus 5 is 25. And this 34. This 20 again I divide by the same procedure. And this contributes to 3 as quotient and 1 as remainder. Now I go to here you can see the double processing. Huh?
I have a small doubt in the previous one. Yeah, here. So normally when we do this 345 by 8, and when you get a reminder of 20, so
remainder of 25. Remainder of 25.
Right, 25. 20 plus 5 is 25. So normally there is a tendency that you divide 25 by 8, and then
this way.
so
The same as 23 have shown. Similarly, you can do. Here also you can subdivide it into, no problem. You can do.
So even that is possible. I mean, can we do that? Because the moment we
You
do
can
25 by 8, it is very easy.
It is very easy.
3 and 1 is remainder.
Yeah, you know it very easy. But yes, you can do this way also, and you know it very easy. So directly you do, no problem. Whatever be the method, and here you have to understand, to make it understand these are also very easy. Right. 23 divided by 8, anybody can do it very easily. Yeah. But it just as a procedure, so that we jump over to bigger things. Before jumping to bigger things, we can do the procedure. Right. Here also you see that 2 here and so 2 here. So the chart, so it becomes 2 to 4. 4, 4. 9 is again 9. This actually this becomes so 9 again becomes, but 9 actually cannot do this method. It becomes 2 and 9, but 9 you cannot do in the big method. These are the shortcoming, you can say. So this becomes 3 and 1. This is equal to 7. These 3 contributed here. So you add to 40. And then 25 become initial 25 right 1. So this way actually It is just to make you accustomed with the procedure. So therefore it is.
Thank you.
Here it comes bigger numbers. So 2 digits, but it requires single processing. So 111 you are dividing by 89. Here also you can just subtract. You can gain that 22 is that becomes remainder, or 1 becomes, you know it. So 1 actually 11 into 1 becomes 11. So you put it down in the remainder directly. So 13 into 2 becomes 26. You put it in that remainder. So 22.
Gautamji, your voice is not coming.
Oh,
Hello, Gautamji, your voice
yes.
is not coming.
Voice now coming.
Voice is okay. Voice is
We
okay.
are not able to hear you.
Okay, okay.
Hello.
Achha, now 89. It is
Gautamji,
nearest.
we are not able to hear you.
No, we can hear you. We can hear.
Is it?
Babu Garu,
Okay then. Oh, sorry.
Some problem is there? There or my audio?
Sorry. My earphone went off. Sorry.
Oh,
Thank you.
okay.
I didn't
no,
notice.
No problem. It happens. Achha, achha, it is 89. It is 11 short from the nearest 10 and nearest power of 10. So 100, it is 11. So you write 11 first. And we work with 11. Instead of dividing 89, even dividing by 89, we first divided by 100. So we put a dash in this case. Here we are dividing by 100. So 111, if you divide it by 100, we put 11 as a remainder and 1 as quotient. Now, because this is 89 is 11 short than 100, this 100 will be contributed. So procedure is that 100 into 1 becomes 11. So this contributes towards remainder. Similarly, 87 is 13 short than 13 short than 100 powers of 10, nearest power of 10. And in 200, 26 actually, because 2 into 13 is 26. So 26 will be contributed out of 200. So this multiply with that. Why I mean using that each 100, 10, all these things are telling. This is an algebraic background, you can say. This is the background procedure. The procedure is one, and to understand the logic behind that, it is I mean this way. So it is not to be. So this 13 into 2 is 26. So it is multiplied, added, and this 48 becomes my remainder. So here also 12 into 3 becomes 36, and then 36 added to the already existing remainder becomes 69. Here it comes to now 3-digit divisor and 4 digits here as a dividend. So 1, 2, 3, 4. So if we divide by 1000, 234 becomes my remainder and 1 becomes quotient. So we dividing line becomes like that initially. And this 888 is 112 short from, 1000 minus 8888 is 112. So it becomes 1 into 112 is 112 contributes to our remainder, and final remainder becomes 346. Similarly, this 211 into 2 becomes 422. So 767 is my remainder. Division by 2 or more digits requiring multiple processing. We'll see here 89, this 1000, 1111, and then how it happens. So you are dividing by 89, and had we divide by 100, our quotient would have been 11 and remainder 11. Now this 11 deficient actually. So first procedure is that 11 into 1 is 11, and you put actually one 11, out of 11, one of the one become this below quotient and other part becomes below remainder. But mind it, it is not actually 1 as it is seen here. Actually, it is 10. It is contributing 10 towards remainder. So therefore, we do not write the 0 here, but while adding, we take it into account. Now then, 1 plus 1 is 2. 2 into 11 becomes 22. 22 goes into remainder. Finally, remainder becomes this 11 plus 22 plus this 10 is 43. We tell it adding like this. 1 plus 2 is 3. 1 plus 1 plus 2 is 4. Like that way. But actually, it is actually 10. So 11 plus 1 is 12. It is clear? So we take another example, 21,456. We divide by 789, which is 211 shorter than 1,000. If we divide by 1,000, it becomes 456 as remainder and 21 as quotient. This 2 into 211 becomes 422. 4 comes here and 22 comes here. Actually, it is 220. It's 2 to 0 actually. Nevertheless, we express it this way. This is the procedure. And 4 plus 1 is 5. This 5 into 211 becomes 1,055. We cannot put this 1 in the quotient side. No. So this is the total remainder side. And then finally we add these 3 numbers. 4 plus 6 plus 5 is 11, 11, 1. 5 plus 2 plus 5 plus 1 is 13. 3. 4 plus 2 plus that 1 is 7, and this 1 is 7. This becomes my quotient, remainder, and 21 plus 4 becomes my quotient, 25. Then this 1731, I told multiple processing. So 1731 requires again to divide like this. 211 becomes 942. Again, that is more than 942 as remainder is more than 789. So this actually here we directly subtract because this cannot be this more than same digit as the same number of digits. Here you cannot. It is totally. If we follow this procedure as if it is totally coming as a remainder, so no, it is not possible by this method by separating quotient and remainder because nothing will be separated here. So you simply subtract. Here is 1 more added towards quotient and this 742 minus 789, 153 becomes my remainder. So this contributed 2, total 2. We add with the earlier obtained quotient becomes 27 as the final quotient and 153 as and as we shift from more and more from the nearest 10, things becomes more and more complicated. 211 into 1 is 211. 21 we write on the quotient side. 1 we actually 100 it becomes. 1 we write towards remainder. This 2 plus 1 is 4. 4 into 211 is 844. We write like this, 8 in the quotient side and 44 means 440 actually is towards remainder. And then 8 plus 1 is 10. 10 into 211 is 2110. It whole thing goes into remainder. Finally, when we add these things. This add towards these things, 150. This is the first part. And again, we 3,106. Here it comes like that. Again, into 3 into 211 becomes 633. Now this becomes 739. It doesn't create any further, doesn't require any further processing. So it is less than this thing. So these 3 gets contributed towards quotient and become finally 153 becomes my quotient and 739 as well. Let me see what is that. Now it requires three steps actually. So 231,456. 231,456 divided by 789. So in conventional division, we would have required a lot of tables with 9, 8, 7, and so on. Here we do not do that. We tell that had we divided by 1,000, 231 would have been my quotient and 456 my remainder. But because it is 211 short, so there should be some procedures. What is that? 211 into 2 becomes 422. 42 becomes my quotient and 2 as a remainder. And 2 in the remainder, but actually 200, I just told. Now, again, this 3 plus 4, 7. 7 into 211 becomes my, what will happen? 7 in this is 1477. We write this 1477 here. But now there is a catch. Actually 7, as I told you, is 770. Now there is a catch. In the next one, I cannot, here see, I am putting this 1 here. I mean, because there is no place to put, so 1 is put here. But actually it goes with this row. In the next processing, I cannot write 1 plus 2 plus 4 only. No. If, we do not multiply by 7 here. We multiply by 14 plus 2 plus 1. How much it is? 17. 17 into 211. Any question? Any question here? So after that we add everything. Now if we add 14, keeping thinking that it is below 4 doesn't matter in the while we are adding quotient side. But in that processing, the 14 has to be added by with 2 and 1 in order to compute this 3587. Now you can 2 plus 1 is 7, this is 4 plus 7 plus 8, this is 5. This total cost, my remainder becomes 50113. Now this becomes 5013, again I do processing, 211 into 5055, this becomes total remainder, this 5 as quotient. And again this 1068 becomes 1 and this. So this becomes this 287 plus this 5, 292, plus this 1, 293. So 287 plus 5 plus 1 becomes 293, and this final remainder becomes my remainder. So this requires three processing, 3 test processing. One is this one is this one, second is this one, and third is this one. The 3 processing. Clear? Now we go to the next one. I was here. Longer complication. 341,567 divided by 654. So here we go to, here we need not, we same procedure we follow, and comes to this one, and first processing is this, second is this 22, third is this, and fourth is this. So final quotient is adding all these things, and final remainder becomes, of course, remainder remains as remainder. So this one. Here any question? Should I follow it? Here see it becomes, this also itself became big. So therefore the complication is coming because of this. The the difference with the nearest 10, the nearest power of 10 becomes more, so that this multiplication are more and so on. So this procedure therefore is not applicable much as we shift from the powers of 10, and so therefore the Vedic methods called straight division is more applicable for this purpose. Or you use conventional. Conventional is one of them. It is also good. It is also very good. So when it becomes smaller digits, so we have a small, bigger, when digits become smaller, we have more difference with the powers of 10. So if the digits become smaller, your conventional method is good for that. So it is you use conventional method. But when we use bigger numbers like this 7, 8, 9, and so on, our difference with the thousands is less. So there, this is more efficient in this procedure. But when these numbers, the divisor itself becomes less in digits, we use conventional method. That is very good actually in this case. But alternately, in the Vedic method, state division also can be used. Now we come to special cases under Nikhilam, where we find that suppose we consider it is actually division by 23 what we, but 23 doesn't come in any formula on that. So what we do, we express 23, multiply it by 4 to place it near it power of 10. So it is actually 92 becomes. So what we do, we divide by 92. Suppose 1011 we are dividing by 92. So we get, what we get here, 8 into this 1 and 0, 8. So 0 and 8 we place like this. 8 contributes, 80 actually contributes towards quotient, and we remainder, and this 91 becomes my full remainder, and 10 becomes my quotient. But this 91 actually is, now we cannot be satisfied with 1011. If we divide by 92, it becomes 10 becomes my quotient, and 91 my remainder. But actually we are not dividing by 92, but we want to divide by 23. So obviously something we are dividing by 92, we get 10 as a quotient. It is 4 times of this thing we are dividing by that. But suppose I do 1/4 times of that divisor, so we obviously get 4 times more quotient. So that is happening. So 4 we multiply by 4. So 40 becomes my quotient, and 91 is my remainder. But 91 was a suitable remainder for 92, but 91 cannot be a remainder for 23. Again, we do. It is not by procedure, this procedure. It is simply by this consideration that 91 actually is 3 into 23 plus 22. So 23, 3 become my quotient here. So this contributes, and 43 becomes my final quotient, and the 22 as well. So any question? Now, I think I expect some question, because now I am changing the topic to another Paravarta method, which is more than the power of 10. So far, we are considering less than power of 10. I think there should be some questions in it.
Yeah, the question is that instead of ready-made calculations, working on a board would help. See, saying all these things is very good.
Oh, acha. Okay. So you give some example.
Yeah.
You give some number for, you say 1, 2, 3, 4, suppose. Okay. Let's take same number divided by 23. Should I? Now here we same thing we do. 92 we do. How do we divide it by 1000? So here is 08 again.
Somebody can prompt. What is the next?
That will be better.
If one of you is following what is being taught,
Tell me.
Rashikar Rao Garu, now since he is doing on board, and you just follow it up and
You
respond.
do it on your pen and paper and tell me.
yeah, you see now, I think they are trying to recollect.
First, forget in this first step. You forget about 23. You as if you are dividing by 92. Very clearly.
I am trying to follow, sir.
Okay. Now you tell me what should I write next, and what thing we write where. First, you have to write what to write and where to write. What to write and where to write.
1 into 08.
1 into 08. But where to write 0 and what to write 8.
And the 100th position and 10th position.
Below 2, below 3, below 4, like
Yes.
this way.
Below 2, 0, below 3, 8.
Below 2, 0, below 2, 8. Now,
Now we have to add these two figures.
no. Because my quotient part is not exhausted.
Sir, 1 minute, sir.
Quotient part is not exhausted.
Pardon me, 1 minute, sir.
Yes.
1, 2, 3, 4 divided by 23.
No.
So why is this 92?
Yeah. So this is the special procedure. First term, 23 into 4, some multiple of 23, because 23 doesn't come much near to any power of 10 so easily. So 23 multiplied by 4 is
4 is 1, 2, 3, 4 digits or last number 4?
1, 2, 3 digits.
4 digits.
4-digit number.
Okay.
1234 I want to divide by 23.
Yes.
So what I do, I express it as a find some number which is near to a power of 10, which is 90.
Okay, understood.
So first we forget about 23 and divide it by 92. Let us see what happens. Then accordingly we will follow the procedure.
Okay.
Now this first step is clear. What is the second step? Because my quotient is not exhausted.
Yeah, 8 into 2. 16. It should be written below 3, below 4, below
3 and below. Exactly. You got it right. Yes. Actually, it requires a lot of some practice actually. Yes. So 1 and 6. Then what do you do? My quotient is exhausted. So there is no further thing is there.
No further quotient.
No further quotient. So simply add. Isn't it? So this becomes 6 4 plus, should I put 0 here? 10. Okay. So 3 plus 8, 11, 12, 13. So this becomes my remainder. And this 12 becomes my quotient. Clear? But this is the result of division by 92. Had we divided by 23, we would have gotten four times the quotient. So 12 into 4. 48 becomes my quotient. But again there is some catch. Here we need not do like this at this stage. So in 130 again, what happens?
That is the 38, 1 and 38.
This becomes, because the 92 again is 92, 8 is there. So 8, this 08 put here. So it becomes 1 and 38. This contributes towards, this contribute, makes it 13. So this becomes 13 and 38. And 38, isn't it? Up to this it comes. It is the result of dividing by 92. This part is not required now, because this will create again another confusion, and we have to again add something here 4 times. So now, so what will happen? Had we divided by 23 instead of 92, we would have gotten 13 into 4, that is 52. Clear? 52 as my quotient. So it becomes 52 as my quotient. But 32 was a good remainder for 92. But is 32 a good remainder for 23? No. So I subtract 38 and 23 is 15. So 52 was my quotient, and then this 1 becomes my 1, another 1 comes here. And 1 and 15. So this becomes 52. Sorry, my pointer. This 52 gets added 1. This 1 becomes 53. And this 15 becomes my and 15 becomes my remainder. $38 you don't have to multiply anything. 30 money remainder. Remainder becomes remainder anyway. But the remainder which was fit for 92 is not a remainder fit for 23, because it is more than the divisor. So the quotient we divide, do these things by quotient we multiply by 4 in this case, and remainder we keeps a remainder, but remainder again we process. Remainder you have to separately again divide by your remainder we divide by 38. In this case, it's simply multiplication by simply subtraction goes actually. Had it been suppose instead of 38, we would have suppose 48. Had it been 48, suppose we got remainder 48, what we would have done?
Then it will be 2 and 2.
2 and 2 would have become 2 and 2 in that case. 48 for 48 remainder. those actually cannot be processing this way because the number of digits, as I told, matching. 23 also 2 digits and 48 also would have been 2 digits. So it is not possible. Simply you do by conventional method. Simply by conventional division. So a hybrid kind of division is required, sometimes with this Vedic method and sometimes by conventional method. So now it is clear. The final result is 53 as quotient and 15 as remainder. Another example, please give me. So I slightly modify this. Let me see what happens, how it happens. Instead of 1, 2, 3, 4, I do it 2, 1, 3, 4 now. Okay. Oh, sorry. 2, 1, 3, 4. Divided by, tell me whose multiplication is near to 100.
Take 23 again, so that
23.
people will be comfortable.
How long you will take more?
I think this will be the last example.
22.
No, 23. you
Okay,
go
23.
ahead.
23 was going. Okay, I was very much practiced with 23. So what you do? This one, isn't it? Near to 100 and multiply by divide by 92. 08. Now please tell me what procedure?
2, 16.
16. What to write what?
Under 1, you write 1. And then 6. Hope I'm right. Yeah. Am I correct?
Yeah, it's correct.
Next is 1 plus 1, 2. 2 into 8, 16. 16 comes below 34.
Exactly. Thank you. Yes. So this kind of participation is very good actually. Now I isn't it? Add no further question is there. So here you do
1,
isn't it?
22.
So here you exhaust all the possibilities with 90. So this becomes again
110 is for 92 is 1 and 18.
1 and 18, isn't it? It becomes 1 and 18. So this becomes 23.
23 and 18.
18.
This into 4.
23
This into 4.
23 into 4.
20 into 4 is 92. Again. So 92.
18, remember.
And there is no much complication is there. 18 is already less than 23. Okay. This became easier. Okay.
Gautamji, can we stop here?
Oh, I have not noticed that. Okay, now my homework. Please show me tomorrow. Say 2, 3, you do 2, 3, 4, 5. Please note down the homework. 2, 3, 4, 5 divided by this 23. 2, 3, 4, 5 divided by 20. Okay.
Only one.
Only one.
Okay.
Okay, what we do is we will ask one of you to work on this.
Yeah.
One of anybody, all will be open. Choose one. We will.
Or suppose again we do another thing. 2, 3, 4, 5. 2, 3, 4, 6 divided by 22. So instead of 23, 22.
Right.
And again, say, it will be less, say 4, 5, 2, 3. It will become bigger actually. Put a 4, 3, not 4, 5. 4, 3, 7, 2 divided by 24. 24. So one is 23. Please note down 2, 3, 4, 5 divided by 23. 2, 3, 4, 6 divided by 22. And 4, 3, 7, 2 divided by 24. Should I practice one bigger digits?
I think this
See,
is sufficient.
1, 2, 3, 4. Another you take a little challenging. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 divided by 23.
Right.
1, 2, 3, 4, 5 divided by 20.
Right.
So four problems. 2, 3, 4, 5 divided by 23, 2, 3, 4, 6 divided by 22, 4, 3, 7, 2 divided by 24, and 1, 2, 3, 4, 5 divided by 23. Please do this homework. I will discuss.
Okay, thank you.
Okay, was the revision okay? Because tomorrow we'll be doing.
Yes,
I think tomorrow's topic should tomorrow revision topic should be easier. Actually, this division was a little, looks complicated by many. Other things are actually divisibility and then divisibility and recurring decimal. You will find it very easy, I tell you. Okay then.
Okay.
We'll close.
Okay.
Yeah, yeah. Prarthana.
We'll go for Prarthana and
Prarthana.
actually tomorrow all of you come prepared. Any one of you may be asked to work on this. Okay.
Also, please go through the presentation so that you can get prepared also with this divisibility and recurring decimal part, and also this Paravarta method. This next one, this part also give have a revision. This
Okay.
one.
Okay.
Instead of positive, this becomes a negative only. There is a difference between the earlier method is that here also negative, here also one this challenging thing is there. Here this half is there. You just get accustomed to that. Why this half actually creating this.
They will go through this also.
There is also one similar to this 24, 23 part. There are also similar things by 20, where we actually instead of multiplying by 2, multiplying by 4, here dividing by 2 in this case. Like
everything
23.
Gautamji, we will go through the complete thing.
So
Yeah,
here just get accustomed with that. We are divided by 2, and how it gave that for this one divided by 2.
Okay.
Will you ask any questions tomorrow?
Okay.
Yeah, all questions tomorrow.
Okay, Gautamji.
Thank you.
No.
Sir, can you please say the homework once again, please?
It is in the video.
You can see the video. He has repeated twice. You can see the video. We are running out of time. Okay.
Only one question. Can I contact you over WhatsApp tomorrow or
Okay.
today? After
At least okay, show it again that I have. गौतम जी एक बार उनको दिखा दीजिए वो नोट करेंगे.
I'll read it out. The questions are.
I'll send by WhatsApp, sir.
Okay, you can send it by WhatsApp. Very good.
Okay, great.
Put it on the WhatsApp.
Okay,
Thank you, sir.
so much. B.R. Simurti garu quickly.
yeah, can I contact you over WhatsApp between 12 to 2 for some clarification?
Okay, your voice is not clear.
Gautam ji,
Tomorrow you ask the question.
Gautam ji, he is asking, can he contact you between 12 and 3 in the afternoon?
You are muted.
I think he says.
Yes, sure, you can contact me.
Right. Thank you.
I'm writing in the chat box.
Right.
Okay, great. Okay, Ananthanji.
These 4 problems we did.
Right.
2, 3, 4, 5 by 23, 2, 3,
Yeah,
4,
it
5 by
will.
22, and 3, 2, 4, 5 by something like that.
Right.
Or 2, 3, 4, 6 by 22. I want 2, 3, 4, 5 by 23. This much.
Thank you so much for the revision. Thank you, sir. Anandanji, please.
ॐ स्वस्ति प्रजाभ्यः परिपालयन्तां न्याय्येन मार्गेण महिं महिषाः गोब्राह्मणेभ्यः शुभमस्तु नित्यं लोकाः समस्ताः सुखिनो भवन्तु काले वर्षतु पर्जन्यः पृथिवी सस्यशालिनी देशोऽयं क्षोभरहितः ब्राह्मणाः सन्तु निर्भयाः अपुत्रः पुत्रिणः सन्तु पौत्रिणः अदनाः सदनाः सन्तु जीवन्तु शरदां शतम् ॐ सर्वे भवन्तु सुखिनः सर्वे सन्तु निरामयाः सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखभाग् भवेत् असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतङ्गमय ॐ शान्तिः ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्तिः हरिः ॐ श्रीगुरुभ्यो नमः हरिः ॐ सर्वेभ्यः नमस्कारः
ధన్యవాదములండి అనంతన్ గారు. Now let us all stand up and recite national anthem, please.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय
Jai.
जय
ధన్యవాదములండి చల్లా చిట్టు గారు.